Okay, so I think it's time to begin this second EVACES webinar. So good morning to all of you, to all the participants in this event. And before introducing our speaker, I would like to use just a few minutes to say some brief words about the EVACES International Association. And so I will share my screen if I can. I think it's not, I'm not allowed, so I ask to Pier Francesco if there is some chance to project some slides. Yes. Okay, so are you seeing my slides now?
Not yet in my case.
So
now we see your screen. Yeah.
okay. No, it's not this one. Sorry. Okay. So just to say that EVACES International Association was informally constituted last EVACES conference in Milan. We have different objectives. First of all, to promote every 2 years the EVACES conference series. But we have the role also to foster collaborations and partnerships between academia and industry to support dissemination activities, to award some special prizes to researchers. I can say that at present, the EVACES International Association has had our colleague, Professor Maria Pina Limangianelli from Politecnico Milano, and we have also other members in the executive board, like Professor Rodrigo Atroza from Chile, Professor Chitang from Saitama University in Japan, Pier Francesco Giordano from Politecnico Milano, and myself from Álvaro Cunha from the University of Porto in Portugal. Our activities are described in our website that you can observe, and from there you can get information in terms of events, in terms of different news. We have also a LinkedIn page from where you can get also information regarding our activities. And as you know, EVACES has constituted a prestigious conference series that began in Bordeaux in 2005, promoted by our colleague Christian Cremona. Afterwards, we had different events in Porto, Portugal 2007, in Wrocław, Poland 2009, in Verona, Italy in 2011, in Ouro Preto in Brazil 2013, in Dubendorf, Switzerland 2015, in San Diego, USA 2017, Nanjing in China 2019, Tokyo, Japan 2021, and finally in 2023 in Milan, Italy. This last conference was chaired by Maria Pina Limangianelli, together with Carmelo Gentile, Marco Belloli, and Alfredo Cicada. The level of participation is described here. So we had 229 participants from about 39 countries, with 25 special sessions and 157 papers included in the conference proceedings that were published by Springer. There was also the chance to promote a special issue entitled Vibration-Based Monitoring of Civil Structures, Innovative Applications and Lessons Learned by the Journal of Civil Structural Health Monitoring. At present, we are organizing the EVACES 2025 that will take place in Porto, Portugal, from the 2nd to the 4th of July 2025. This event is shared by myself with the collaboration of my colleague Elsa Caetano. And you can get information about this conference using this link, this webpage. I can say that at present we have collected more than 300 accepted papers, and we have 6 interesting keynote lectures. And the scientific committee is composed by many prestigious researchers in the field. Just a final note, EVACES International Association has also a concern to have a good link with the industrial component. So you have an industrial committee constituted by members from STRAM, from Kinemetrics, Devasoft, and Structural Vibration Solutions at present. So in the context of our activities, we have the honor to have today with us Professor Eleni Chatzi in this second webinar of the series. I can say that Eleni Chatzi is a full professor and chair of structural mechanics and monitoring at the Institute of Structural Engineering of the Department of Civil, Environmental and Geomatic Engineering of ETH Zürich. She currently serves as the president of the European Academy of Wind Energy. Her research interests include the fields of structural health monitoring, hybrid modeling for digital twinning, and data-driven decision support for engineered systems. Her work in the domain of self-aware infrastructure was recognized with the 2016 ERC Starting Grant Award, the 2020 ASC Uber Research Prize, the 2020 EAST Junior Research Prize in the area of computational structural dynamics, and the 2024 SHM Person of the Year Award. So thank you very much, Eleni, for your availability. And before giving you the stage, I just would like to make a final note. It's natural that the participants that attend the webinar have some questions, and if that is the case, please don't hesitate to put those questions through the chat, and at the final I will try to read these questions and put them to Eleni. So please, Eleni, thank you very much once again, and the stage is yours.
Thank you also on my end for the very nice introduction. Let me see if I can share the right screen. Probably it should be that you can see it in full now.
Okay.
That's great. So I would like to give you a bit of an overview of the research we conduct in my group at the Chair of Structural Mechanics and Monitoring at ETH Zurich, using what is mostly based on physics-based principles for the understanding and monitoring of different types of engineered systems. The main approach that we follow in this respect is to treat these engineered systems not as inanimate, but in a sense, as self-aware systems. This was mentioned also earlier for one of the awards. Self-awareness now being a trait that is somehow linked to their nature as what we would call cyber-physical systems. And I am referring to cyber-physical systems because these kinds of structures and infrastructures that we are today running have the capability to feature different types of sensor installations that are revealing about their performance and about the way in which we can best manage them. So if we were to simplistically somehow try and reflect the operation of these systems, then we would have them operating under various disruptive agents, which are, of course, somehow trying to compromise the physical asset. But we have today the option of using different types of sensors that come at various costs and various types of precision, delivering different types of monitored information, including dynamic and static information, optical, vibration-based, and whatnot. And we can use this information to build the digital representation of these assets in a way that it is a true digital twin interacting with the system, which is something that can then be used for decision support in terms of assessment, but also interventions and repairs, not only for the individual asset, but also for the collection of these assets in what we would call a system or a fleet. So I mentioned data as one of the, extracting this kind of data as a main means of information for better understanding and modeling these systems. And it is true today, we imagine availability of data to exist in various domains influencing the activity of these systems, including the loads and stressors, the environments that are actually acting onto the system that are usually varying in nature and not easy to model. The structures themselves, which we as engineers have a way to model, but which are never necessarily materialized as designed. And therefore, it is of great importance to be able to track the as-built system, which is a truly operating system. And of course, we have the potential, if we have deployed instrumentations that are usually continuously functioning, which is more of the character of structural health monitoring, to also monitor disruptions. So we can actually track important information about the operation of these systems, which is also what I will be using today for my examples. Specifically coming to our examples, I would like to mention a bit the ways in which our chair is able to extract different information for various types of assets, starting with transport infrastructure and railway assets in particular, where through various previous projects and collaborations with the Swiss Federal Railways, we have been exploring the concept of indirect or onboard monitoring, where you can use information that comes from sensors that are actually mounted on the movable side, so the vehicle side, to understand the performance of the infrastructure that is being traversed. We also have activities in the domain of wind energy infrastructure. Amongst various projects, we also own a small-scale wind turbine, which is not too far from our campus and which we treat as a living lab for implementing different types of technologies and for understanding the performance of the methods that we develop. Of course, we also have activities in more traditional types of infrastructure, including buildings and bridges that we have monitored as benchmarks in the past, also for understanding the way in which damage can be picked up from various types of sensing information. And as always, as we're in the field of condition monitoring, engineered assets, also machine-based components are actually within the agenda that we try to pursue. So I would like to show you within this kind of context what it is we do with data alone first, because there is a lot that we can learn from data as long as we can actually recognize the limitations that are involved. In this picture, I'm borrowing the example of wind energy infrastructure, which I mentioned we have a number of activities on, to show you how we can use data to model complex effects, such as the effect that you see here in this now famous picture, which is the effect of wakes. Wakes are traveling vortices that are created on the blades, and they affect the downstream turbines in terms of the power production, the resulting vibration, the turbulence, the experience, and therefore the loads. So here, by using SCADA information, meaning data from the nacelle, the top of each and every one of these turbines as they are gathered throughout their operation, we try to produce a data-driven model that shows, using as input only the mean meteorological conditions on the site, which are usually delivered by a MetMask model, what is the performance of these systems? What is the performance in terms of the wind that they experience, which is something we're able to reproduce, but also more informative engineering quantities that have a straight connotation or a direct connotation to the experienced damage loads and fatigue of these systems, such as, for example, here, the wake deficit. We're able to do this in this case using a conditional variational autoencoder, which is a machine learning model learning from data, which exploits, however, I should say, this is one of our earliest works, it exploits already a graph structure. So we are feeding here some information about the system, primarily about the geometry of the system. And this is what enables us to have such a prediction, even for example, this kind of damage equivalent loads, which are usually engineering quantities of engineering interest. The problem, however, with such a model is that it is only as good as the data that it has seen. The moment we have a situation where we experience information that is outside of the field of training, we start having difficulties. And this is why we say that data is in fact not enough, or at least this is what we advocate in our group. We try to use data as an initiating premise. We know that purely data-driven representations can give us insights. Actually, oftentimes they excel at tasks that have to do with diagnostics, for example. But the moment you want to go a step further, you have to bring physics and overall understanding into the loop. And this is not new for engineers. We have been using physics for years, but usually we use it in what we call the as-designed system. You use it to design the system and predict and anticipate its behavior, not necessarily connecting this with data. And what we would like to achieve here within the context I am describing is the hybrid functionality, the situation where physics and data come together in a hybrid construct, which is, if possible, able to compute very fast on the fly as data is attained, creating interactive closed loop digital twin representations that can really reflect the system as is operating and therefore advise us on how to best react next in a short or long-term horizon. If you would like to express this problem in the context that we're facing, then we have to admit that it is actually a quite complex problem, especially if we're thinking about real-time digital twinning, which is really the main goal for our activities here at the chair. Since we have systems that are complex in nature, in that they're actually characterized by nonlinear dynamics, they are responding to loads that could be environments that are varying, that are not easy to monitor. They have acting loads such as waves, wind, or traffic that is distributed in nature, not easy to track in a very accurate manner. And we're gathering data, but this data is sparse, and it is in select locations that we have the ability to instrument. And at the same time, we have to comply, we have to balance this data with engineering models that are usually overly complex and not easy to reduce in terms of computation. So this is what we will try to do here. And I'll try to show you examples that try to achieve this for the tasks of digital twinning and reduced order modeling, data-driven diagnostics and prognosis, but even tasks that really require very fast reactions, such as, for example, control and eventually decision support. Now, maybe before I proceed, it's good to say that together with some of my colleagues in a recent paper, which you now find available in the Journal of ASE, ASME, Risk and Uncertainty for Engineering Systems, you will find that we try to actually frame these various uncertainties that are underlying the behavior of these systems and try to break it down to the usual construct of how we describe these dynamic systems, because the systems we deal with are usually dynamic in nature. This is where we think most rich information can come from. So here we try to break the uncertainty into the parts of the problem, from the input uncertainty to the model uncertainty that could be about modeling error, but also parameter uncertainty when some specific prior knowledge of the model is at hand. Confounding influences or aging processes that are actually acting onto the system, making it harder for us to model its behavior, but also uncertainties that have to do with the measured output, which can never be precisely measured. And you will see different methods that we actually describe for tackling these. Now, given this kind of problem statement, which is quite complex, I want to come back to the actual utilization of the physics. And I remind you that the goal is to use engineering models, but that actually the classical models that we as engineers tend to use are not necessarily the right models, because their complexity often makes them inadequate for the fusion with data. I give you examples of such models because, of course, as a chair and a group, we teach also these methods for fundamental engineering problems. But I remind you that actually what we would like to have in the end is something that can compute in fragments of a second for the types of problems that we're dealing with. And I'll show you some examples also later on, but you wish to have simulations of complex, maybe cracked and defect geometries that are dynamic in nature and really, really fast to compute. There exist today different ways, of course, of doing this. All of you are familiar, I think, with reduced order modeling strategies, or what we typically call surrogates or metamodels. Now, in our context, the most useful of these surrogates are those who can always have or refurbish a connection to the original full order model. And I show you what I mean here with an example by the work of Tom Simpson. Here I'm showing you the example of a possibly detailed finite element model of a large number of degrees of freedom, which we use for dynamic analysis. And the logic which we follow often for reduction, or which we can follow for reduction, is the following: not to use the original set of degrees of freedom, but to try to reduce these by using appropriate latent space representations. Sometimes for linear systems, for example, you would know this as the model representation of the system. Now, because we're discussing nonlinear systems, we have to use alternate methods to derive these features. And here we use a variational autoencoder, which allows us to extract a low-dimensional space where we implement the acting loads to the system. And this is where we're actually implementing also the integration of the system in time. This can be done with your favorite integrator. In this case, we use also a machine learning algorithm to do the integration, an LSTM in this particular case. Now, what is important in this kind of surrogate framework is that at any point in time, and even though this is a nonlinear system, we can go back to the original space using the decoder function of our autoencoder construct. And this allows us to recover the response of the system in the original full order degrees of freedom. The reason why for us this is important is because the quantities that we measure, whether these are strains or displacements, velocities or accelerations, are in the original degrees of freedom and not in this reduced space. You can imagine it as a model space, which doesn't necessarily have a physics connotation. So we need this kind of a framework to be able to proceed. We have actually corroborated this framework in the by now quite well-known benchmark of the nonlinear frame of the Los Alamos National Laboratory. It is a frame featuring a bumper, a nonlinear element. And here it is quite hard to show that you can get a good feature extraction, meaning a reduced space where the components are somehow independent, which is the goal, to produce what we would call an approximation of nonlinear normal modes. And we show that with the variational autoencoder, it is in fact possible to succeed in such monochromatic, almost monochromatic and thus individual components. More importantly for us, we took this developed reduced order model and we implemented it on an actual engineering problem offered to us by our collaborators in Siemens Gamesa, a monopile wind turbine structure, which is actually based on nonlinear soil, on foundation that is soil, which has a nonlinear behavior, characterized by the so-called PY curves. And this kind of computational model is actually very difficult to compute for transient and steady state effects for nonlinear analysis that are of dynamic nature. So we try to implement this kind of approach to give them a surrogate that can produce the same result in all degrees of freedom of the model, therefore including the degrees of freedom of interest, but at fractions of the computational time, in fact, in real time of computation. Now, in what I've shown you, I make the point of reduction, but I don't discuss something quite important, which is what happens when you want to produce these surrogate models, not only for a single instance of the system, but for various different parameters of the system. For example, what if I had different soil conditions? Can I produce a reduced order model that is thoroughly comprehensive and can also be conditioned on these different various parameters? And the answer is yes, there exist ways to do that. And one of the favorite ways in which we try to implement this is by producing what are called projection-based reduced order models. I show you here a way in which this is achieved by using a benchmark structure from civil engineering. This is let's say, a popular favorite, a shear frame structure, which is excited by earthquake. It is also a nonlinear structure because every joint here on the shear frame is a hysteretic joint, meaning it has nonlinear behavior post-yield. It is characterized by a Book-Wen hysteretic model, which is a convenient model for us to deploy for finite element approximations. And it is excited by ground motion, which can be characterized in terms of parameters, both in the frequency and the time domain. So we can actually break down an earthquake excitation into its parameters, which will be defining our problem. And we also have a characterization of the system by a set of parameters that correspond to its linear behavior, for example, the Young's modulus, or its nonlinear behavior, for example, the Bookman model characteristics. So here's the question: how do I produce a fast computing surrogate, a reduced order model that respects the physics, can reproduce the response densely at every degree of freedom, and condition it on these parameters? The way to do it is to use a projection-based approach where your original equations of the problem can actually be transformed into similar nonlinear finite element equations, but now using a variable, a new variable, which is of much lesser dimension, of a dimension r, that is much lower than the original n degrees of freedom. The way this can be achieved is through a transformation of the original variable by using a projection matrix to a reduced space. And this projection matrix is something that we can extract from running multiple simulations of the original full order model. So we take the time histories, we implement essentially a singular value decomposition conditioned on different parameters, and we're able to extract these projection bases. Now, traditionally, this extraction has to be for it to be efficient, you should be repeating it for different types of parameters of the input or of the characteristics of the structure. It wouldn't work so well if you do it for any type of, because you could do that, you could produce such a global basis, but it wouldn't work so efficiently. And there is a problem here in this construct because it doesn't really give us a functional dependence between parameters and these very important bases. And we actually corrected this. We have introduced with Kostas Vlachas a procedure to reproduce these kinds of reduction bases just by defining the set of the parameters that are governing the problem, and we are able to do it in a stochastic way, which is succeeded through the use of conditional variational autoencoder once more. Where given the parameters of the problem xi, we're able to retrieve the local basis of our projection and get very successfully a reduced order model that is very efficient in the way it approximates the problem. In fact, going a step further, although for the simple example, our parameters are the parameters of the input and the stiffness parameters of the problem, you can move one step further and use conditioning parameters that are actually coming from monitored features, which is more realistic. Instead of physical parameters, parameters that can be extracted through monitoring. You can check this out in this most recent paper. But here I show you the principle of this approximation. So given the parametric space, for example, here imagine the amplitude and frequency content of your earthquake excitation, you can produce for all of these situations that reflect different nonlinear response traits through your surrogate approximation, a very good or sufficiently good approximation of the problem, of course, with varying degrees of efficiency. And this is something you need to know when you're using a surrogate. A surrogate is an approximation. A reduced order model is an approximation. So what is important for us as engineers is to define the threshold where we accept a possible error, which is what we did here. And you see that we get a sufficient approximation of the quantities of interest that are the dynamic response time histories at different degrees of freedom of the system. Because we're using an approach for a reduction that employs the variational autoencoder for producing the basis, we also have a stochastic tool that can give us some uncertainty bounds about what is the error associated with our approximation. And this is what you see here. So we don't just have a deterministic estimate, but also a way to quantify the probable error that is induced from this approximation, this reduction of the full order model. Up until this point, I have discussed how to reduce models so that they can be used with data, and now we'll also give you a brief overview on how we can fuse these models with data, which in our group, again, we claim can be done in various ways, depending on the confidence that you can attribute to physics, which is your model. So if you have strong confidence, you can even use a white box, a perfect model. Or if you don't have strong confidence, you have to rely more on data. So you could use a black box model in the worst case when you have no knowledge of the physics. In practice, what happens is that we're somewhere in between. And so really what we're doing is we're navigating a spectrum that depends on how much contribution we allow from the model and how much from the data. In this plot, you see different methods that we have mapped, and we also offer a library for these tools, but I will come to that later. First, I would prefer to start from explaining the white box approach, or close to the white box approach, which is what happens when you can really assume you have a well-performing model. In that case, assume I have the reduced order models that I used earlier, which were well prepared to simulate the system. You can always bring your problem into the so-called state space form, where you have a dynamic equation here in continuous or discrete form, and an observation equation that complements it because you have data that is extracted from the problem. And you have, of course, the model, usually reduced order model, that is enabling these two equations. But these models and the data themselves, they suffer from uncertainties, as I explained earlier, uncertainties due to approximation, due to the measurement errors and whatnot. What we can do is to exploit this kind of dynamic model in a Bayesian construct. And this is what we will do here. We will use our models in a Bayesian filtering context. And this is how this works. In Bayesian filtering, we assume that the response of the system, which is our state, is a stochastic variable that can be approximated for nonlinear problems by a set of discrete points that are actually capturing the mean and variance of our response. The state is usually the displacement and velocity, for example. If this is how we approximate the state at time tk minus 1, we then pass it through the equations of the problem, the reduced order model in our case, to get the response of the system or an estimate of that response at the next point in time by propagating these points through the nonlinear function and then getting their statistics. Now, additional to that, we also have the benefit of monitoring. So here we can use data, understand by getting the estimate of our measured quantities, how far our prediction is from the truth, and correct for that discrepancy to get an optimized posterior, optimized in the Bayesian sense, that tries to bring a balance between the model of the system, the reduced order model again in our case, and the data and measurements that we have been collecting. So it's always about this sort of exercise in balance, how much of the physics and how much of the data contributes to our estimate of the response. This is the rough description of the framework. There is a lot more math that goes into this, which you will now, you can find in our recent publication, where we overview different methods for extracting just an updated estimate of the response of the system. When the system has unknown parameters in its description, you can also estimate these parameters in a joint state parameter context. If the input to the system is unknown, there is also a way to estimate the input to the system, provided you have appropriate observations, or you can try to do everything everywhere all at once, input, state, and parameter estimation, which is again possible provided that the laws or the conditions of observability, identifiability, and invertibility are respected. We have produced different types of versions of these algorithms, even for challenging problems like non-smooth problems or problems with distributed inputs and parameters, for example. And you will find them in this recent tutorial paper, which is completely open access and comes together with a code, a library in Python that explains how to use different types of Bayesian filters depending on the task that you wish to achieve. However, a big assumption there in this kind of framework was that the model was quite well formulated. The model error, therefore, is quite low. Let me show you here an example on an application. This is the case where we try to approximate the behavior of the fuselage, which is a shell structure, which we assume could have different types of damages in the form of cracks. And we try to monitor this by using a limited set of sensors here in red. And we're also trying to deliver a digital twin, so we want to predict the response of the system also in the green locations, which are not observed. So I'll treat this as a reduced order modeling problem, but the parameters now are the possible positions of the crack. This makes it a non-smooth problem. In order to solve this problem, you have to bring in again your engineering intuition. We use a trick from mechanics, computational mechanics, which is mesh morphing, to use a fixed number of degrees of freedom, but morph the mesh even for curved geometries so that we can represent different types of cracks in different positions and orientations within our original geometry. By doing this, we're able to then use the reduced order model, which computes very fast, put it inside a Bayesian filter estimation that assumes that the inputs are unknown and treats them stochastically, but also the parameters are unknown and should be estimated. We formulate a sort of nested optimization type of loop, and we're able in the end to extract estimates both for the parameters, the location, orientation, and placement of the crack as the analysis proceeds, but also, more importantly for us, perhaps, we're able to reproduce the response of the system in virtual sensing positions, in positions that are not being measured with quite high accuracy. All of this worked because we have a high fidelity model. It worked very well because also we have a very good speed up through our reduction. We also showed through partnership that this can be implemented on real structures. Here you see former PhD student of my group, Silvia Vettori. We implemented this approach in a project led by DTU, where you see the experimentation on a wind turbine blade, which is outfitted with different types of sensors, accelerometers and strain gauges in this case. And what she did was to use a model of the system that is a reduced order model. She used substructuring for that, for the blade model. And she used a Bayesian filter, an augmented Kalman filter in her case, to combine the data from the sensors with the model predictions to deliver a surrogate that can actually then feed visualization tools that are not produced by us, but by Siemens Industry Software in this case, where Silvia was also a member of. But you can see here the sort of augmented reality logic, which brings the predictions, the very fast prediction of such a surrogate to the laptop of an engineer so that they can then, at a full field estimate of the strain on this blade, so that they can then proceed with any desired downstream task, whether this is diagnosis of damage at the current stage or even reliability indicators about the fatigue accumulation given new loads, and understand robustness of the system, reconfigurability, and all of the aspects of resilience. For us, it is very important to deliver such frameworks that are motivated by real-world situations, and this is also the case for two spin-offs of our group, RTDT Laboratories AG and IRMOS Technologies, that are now implementing these concepts on wind energy and transport infrastructure assets. What I failed to explain, though, earlier, but I sort of left it for later, is the more intricate complexity. So what if I don't have a model that is very well able to represent the behavior of the system? Maybe I have errors that are bigger or greater in the form of what we would call model mismatch or model form error, because we have phenomena that cannot easily be modeled by physics-based terms, because we have systems that are being, for example, largely traversed by our sensors, and we cannot actually anticipate to have their detailed model. What happens in that case? In that case, you have to start going down the diagonal of the previous spectrum, and you have to trust data more and more into your simulation without, however, abandoning the physics. This is what we explain in a recent paper on physics-enhanced machine learning, where we explain the aspects of navigating the spectrum depending on the balance you wish to keep between physics and data. And there you will find both the paper, but also the code, again in Python, offering different types of implementations for basic algorithms that we have experimented with. You also will find some of the algorithms that we have developed as part of this effort, which you see summarized here, and which we could cluster in terms of the way in which they impose the physics into physics-guided, physics-encoded, and physics-informed schemes. All of them we cluster under the prism of physics-enhanced machine learning, with the difference being the following. In physics-guided schemes, we try to put the equations of the physics explicitly into the transition and emission functions of the neural network architectures that we use. In physics-encoded schemes, the architecture of the neural network itself is made to be a differentiator or is made to be an integrator that respects physics, such as Hamiltonian principles. So the architecture encodes the physics in a way. Or you may have physics-informed schemes which more loosely actually implement the physics just by having it as a loss function where you express your desired equations that have to be satisfied and the desired constraints. All of these bring different flavors into the approximation, and they depend on the problem which you have at hand. One of the favorite ways in which we try to do this kind of mixing is with this physics-guided approach. We love to be able to feed the equations explicitly into the formulation whenever this is possible. And you can imagine this, although it is not necessary to see it as so. But one way to imagine it is as a superposition. So imagine you have a system for which some physics is available, a simple model, even an empirical model, and a system where also some data becomes available. It is possible to create a construct that uses part of the physics and complements it with learning a model from the data, for example, a model of the discrepancy, so that you can best approximate this system. I show you here an example using a very basic nonlinear system that is a pendulum, assuming that the observations we have are images, for example, frames of a video. And this is the nice thing about learning from data with these algorithms. Actually, it can be done in very loose ways. Here we're using a deep Markov model to do this kind of approximation. So we feed the model with these image-based observations, and we also say, we let the model know that we have a very basic reduced order model that is approximating the physics. We're using the linearized model of the pendulum, which is not actually appropriate, it's not complete. By doing this kind of deep Markov model that is conditioned on the physics, by using it, we're able to reproduce here on the left in blue the response of the system in terms of the full states, the angle of the pendulum and the velocity of that angle in a way that respects the physics, the phase space that we expect. Where if you're to use the purely black box model, the deep Markov model, you would not be able to infer something like this. You would infer this sort of erratic trajectory in blue. And this is because the black box model has no obligation to know the physics. It doesn't know through the linearized equations that you expect the derivative to be the next state. But this means that it can also not predict it for you. So it can only predict what it observes, which is not so useful for us at the end of the day. We have implemented this then on practical use cases, actually also on the example of drive-by monitoring. I already referenced this example where we use sensors on trains or cars, so different vehicles, to collect information on the basis of vibration and to indirectly in this way monitor the traversed infrastructure. We do this both with collaborators in Singapore and in Switzerland. And here is that principle. You have a rudimentary model of the vehicle, which actually is not precise, and you try to learn the rest, the model error perhaps, through the data that you collect. By doing this on different types of surfaces, in the beginning on flat and surfaces that do not, for example, have roughness, you're able to get an updated model of the system, which can then be used to understand, for example, inputs to this system, as is, for instance, the roughness of the roadway pavement. And this is for us a quantity of interest when we do mobile sensing. We want to recover this roughness because it's an indicator of the performance of the road and the way it has been constructed. We show that by using this physics-guided model and having different weights to fuse the physics and the data, you can have different levels of approximation. The optimal approximation is actually learned by the algorithm. I'm just here forcing the different levels to show you that there exists such an optimum balance. We have been implementing such principles also on real-world case studies, such as, for example, in a recent project with a state in India, where we use these instrumented vehicles to extract the international road roughness indicator. We also do it with trains in a project with Harastura, where she uses the sensors on the axle boxes of train vehicles to understand modal properties of bridges in an indirect manner. There she's not using the physics-guided deep Markov model, but the process that is again based on a Bayesian filter, such as the one I discussed earlier. Now, there is a part I wanted to squeeze in here, but I think we don't have enough time for this, and therefore I will only briefly refer to this, which is what happens if you want to discover meaningful representations of the physics that the neural network fits. And this is possible. We show it for a use case of an experiment here of a nonlinear shear frame outfitted with a negative stiffness damper, which is a nonlinear mechanism. Here we claimed we knew only the linear behavior of the system, and we tried to recover the behavior of the damper through the neural network, which we do, but then it's approximated by a black box model in a sense. If you want to transparentize, as we would call it, decipher this learned neural network, it is possible. And you can do it by trying to fit expressions, grammar-based expressions that try to approximate the learned equations. There exists a very well-known tool for doing this in nonlinear dynamics, which is Cindy. And indeed, we tried this for this example, showing that yes, You can recover an approximation that sort of gives you an equation of how this damper behaves, but we try to then also improve this tool because when you use such dictionaries, it can be quite restrictive. You really have to specify the terms that you believe are feasible to describe the problem. We want it to be a bit more loose, more flexible. And in this recent paper with colleagues at ETH Zürich, the paper is led by George Kissas, we show how to use formal grammars, which are tree constructs with symbolic expressions, to fit inverse problems, such as, for example, the discovery of constitutive laws, of material laws from dense observations that could be DIC measurements, for example. I don't have the time to go over this, so I will skip this portion, but I would like to tell you that we're now extending it for approximating also differential equations, so not just constitutive laws, in work that you will see coming up soon from Karin Yu and George Kissas. And finally, I want to close with what we think you can do next with these methods that we try to develop. And what we think you can do next is try and assess at the system level, at the network level. So you can take these principles of using these low-cost, usually sensors with diverse information, such as, for example, acceleration and GPS. In our case, we have outfitted these on movable platforms that don't need to be vehicles. In fact, we have done this also on robotic vehicles of a very small scale, such as the one that you see here. It's the so-called RoboMaster. We use this simple vehicle to traverse the shoulders of bridges and extract information about their behavior, about their dynamics. We use these kinds of sensors on bicycles, and we ask volunteers to use them to traverse bicycle pathways so that we can extract information on the roughness of the pathways, possible defects, and holes that are somehow compromising the condition of these assets. And then we try to map them at the network level. This is sort of the principle we wish to follow. This is the principle we follow also with our assessment of railway infrastructure with Giacomo Arcieri. We're using indicators that come from diagnostic vehicles of trains that offer information about the situation of the rails and the subsoil, the ballast. And based on these monitoring information, we have collected 10 years of such observations from the diagnostic vehicle. We're building a model of the system, a model of its deterioration. It's a stochastic model. It's a partially observable Markov decision process because our observations are incomplete and indirect. And together with information from the experts about the cost of intervention strategies and how they impacted the system in our observed data from the past, we're able to build strategies on how to best manage these assets given observations in the next years to come. So you have now the new inspection information from the diagnostic vehicle, how to use it, what would be the best way to use it to minimize your expected costs for maintenance in the next foreseeable future or the horizon that is of interest. This is a problem, an optimization problem that can be solved mathematically and is explained in the recent works of Giacomo. I don't want to give you more details because I sort of extended my time. I just want to close with this kind of a vision slide that explains the process that we follow from collection of data to augmentation with physics intuition and engineering knowledge and the corresponding models, with interaction and information from the experts about how the system performs and what are the costs that are associated with different types of actions, to best understand how to deliver predictive tools at the level of the ecosystem, which is the network level. With this, I would like to close and thank you very much for your attention.
Thank you very much, Eleni. After this so much interesting talk, I'd like now to look at the chat and see the questions that appeared. We have a first question from Anshu Sharma. He says, good morning. I have recently started my research in the area of physics-informed neural networks for structural health monitoring. I'd love to hear some advice to move in this area.
Yes, so our experience with physics-informed neural networks is that it is a very potent tool for solving equations. When you have an expression of the equation of the problem and some data, because it can be used to do a balance of the two, but you have to know that it is an instance modeler. The pin tries to solve the equation of the problem as a finite element model would. The reason why it is of interest is because it tries to do it in the continuous space and not the discrete space of the finite element model. Oftentimes, and there have been papers that show this, the pin can be very slow, actually sometimes slower than your FEM model. But the benefit, therefore, of its use is to use it in an inverse context, in my opinion, to use it to identify parameters because they can also be inferred during the optimization process so that you can have a good compliance, a good balance between the solution of the physics equation, which is in the loss, and the data that has to be respected that you can also feed into the loss. This is where it's particularly strong. Now, there are also ways to reduce the computation of a pin. And one of our recent scholars in the group, Rui Zhang, has delivered such a method that tries to break down, to discretize the domain of the pin, the time and the space domain to do this. So there are many advancements that can be considered in our context. And so I consider it a field where you can have you can find room for contribution, but you have to do it in a way that understands the principle in which the pin operates, the limitation of this instance modeler. This is sort of the input I would be able to give.
Okay. We have then a second question from Eleonora Morleo. She says, thanks, Professor Chatzi, for the insightful presentation. I was wondering whether it would be possible to leverage a physics-guided approach, especially in cases where a fully reliable physical model is not available, but a large amount of data is, to estimate the response at an unmeasured point, similar to what you did with the morphed mesh in the fuselage study.
Yes, this is the point. So I was explaining that depending on how much trust you have in the model or the data, you can weigh them in different ways, actually. But you can always have a model of the system, even if it is rudimentary, and sometimes even if it is slightly false, you can actually use it to bring predictive quantities in the latent space that are physical. Because otherwise, with black box models, what you get as a latent space prediction has no meaning. You cannot do virtual sensing with black box models. You can do virtual sensing even with slightly wrong physics-based models, provided you correct them with the additional term that accounts for the data, the term that will try to account for modeling error, essentially. So the answer is yes. And what I showed is a way to sort of go in that direction.
Okay. Well, I don't see other questions here in the chat. I'd like just to say the following. I think it's amazing the wide range of development you and your group have made, theoretical developments, experimental development, fusion of
Oh,
data.
thank you for saying this, but for experimental developments, we're looking at your groups,
No,
actually.
no,
we try because we need real data. We need them to
yes,
show that things work.
okay.
And we're sort of forced, I think, all of us in this domain, we have to take into account, this is the way we work, real data, experiments, field data, but also the models. I mean, we're all engineers trying to approximate the problem, which is what causes this kind of spectrum to be necessary.
You have managed to make a wide range of applications from railway infrastructures to buildings and bridges to wind turbines to other applications outside civil engineering. I just would like to ask you, are the developments you are really more proud of at this moment, taking into account the real impact that these developments can have in terms of the industrial interests, in terms of the
Yes.
interests of the civil engineering market?
I can reply to this because it's something I have been working on for a while. I realize that from a practical viewpoint, our methods are not so meaningful unless we can translate them into something that is exploitable by engineers. And this is why you see, as the last element, I showed the aspect of decision support. Without this element, we do not have the arguments and the convincing power to explain why these technologies and methods are important. And so for me, to always try and tie these indicators to ways in which I can support decision, I can support policy making, I can inform operators about the value of information that comes from monitoring is a big, it's a sort of an aspect we devote ourselves to because it is the means I believe we have as scientists to bring our methods into practice, to transfer them in an actionable manner. And I consider this element as something that is indispensable, and I try to sort of carefully bring it in to our activities, which otherwise would be could be limited to just the predictive side, just the indicator construction side. But I found that it's not so convincing to just leave it there. You have to show people how it can be used, and that's why I think this aspect is important, should be considered.
In the meanwhile, we have got two other questions. First from Sagar Bansal. Hi, this is Sagar Bansal, PhD scholar from India, working in the area of PHM. I found most of the open source data sets are unlabeled, means ground truths are not
Absolutely
given.
true. Yeah.
If we rely on digital twins for data generation, then we are not able to generate proper real-time data.
I can reply to this. It is true. Most of the data we have in SHM, not so much in PHM, because in PHM you have experiments to failure very often for gearboxes, for engines, which is a special situation. In SHM, you do not have labeled data. We are not going to test our bridges to failure. We just put them there and we let them operate, okay? Which is why it is very important to bring the model in the loop, because you don't otherwise have predictive power just from the operational data you have. This is the whole point of bringing the model in the loop, because our schemes have to be largely unsupervised in SHM. It is very rare that we will have labels of damage, because that's our purpose as civil engineers. We want to avoid damage. We want to avoid collapse. We want to avoid creating such labels. And this is the main motivation behind why you see me bringing the physics into the loop, to be able to allow prediction in an unsupervised or less strictly supervised manner. And we don't claim that the digital twin will create labels either. We just try to always balance the two, the prediction of the twin with the data as it is attained. Okay, this is the best we can do for many of these systems. We cannot wait for them to fail to get the data failure, but we're able to see them as they progress towards failure using these tools.
Okay, we have still a last question from Daria Nikolaeva. Thanks a lot for presentation. What would be an advice to perform an effective transition from fully model-based approach to data-driven or hybrid?
So for us, if you're asking in our case, the beginning into this already 15 years ago, or a bit more now for me, is this logic of Bayesian, the Bayesian logic, okay? I think it's a very powerful theoretical tool for bringing this balance, the scales that I showed between model prediction, which is a sort of prior, and the likelihood, which is how close are you to the observed evidence and data. It is more or less this kind of approach we follow in many of our constructs, whether these are the Bayesian filters, or even later on in the deep Markov model, which is a type of Bayesian filter, we use a variational approach, which has a similar logic of trying to balance the prediction of the model with the data we have at hand. So it is a bit of a balancing act. And these kinds of theories are there to allow us to do it.
Okay, a last question from Cassio Gaspar. Thank you very much for your nice presentation. Considering the 4 levels of Ritter's classification for damage identification, which level are you achieving today?
Well, we make a point of trying to achieve all of these levels. That's why I showed this example with the blade, where, for example, if you had that digital twin, you're able to use develop diagnostic indicators, which is often easy to do even with just data of whether damage exists in the system. That's usually also a purely data-driven task. To go a step further, to localize damage, for example, to find where the crack is and what the orientation is, you need the physics. So this is why we bring physics in to also achieve the next levels of SHM. And virtual sensing, which was the main task I was focusing on for real-time digital twinning, is precisely for achieving the final step. You have a functional twin that can accept new loads and can predict for you in the future what is the performance of the system, what is the remaining useful life, which is the 4th and final level, and impossible to reach with black box or purely data-driven models. It's actually precisely probably I could even use it as a motivation within the slides. This kind of Ritter scale is a main motivation behind resolving in these kinds of methods.
Okay, so at the moment we have no additional questions. If no other question arrives, I think it's time to close, and thank very, very much to Eleni, the availability to be here today with us. I'm quite sure that this has been very fruitful for all the attendees of this event. And so thank you very much.
Thank you for the invitation. It's always a pleasure to see you.
Okay. So I hope also that the attendees are interested to continue participating in our future webinars. I'm sure of that. And so I will close the session here. Thank you very much, Eleni. Thank you very much, all of you.
Have a good day. Bye-bye.
Have a good day. Bye.